So we now know that in an exponential function, the variable is in the exponent. So how does that then change when we do some calculations? And what happens if I want to graph an exponential function? So let's go ahead and check that out at the top of the next page. So first off, I'm going to go ahead and talk about how to do some calculations. So in order to think about that, I'm going to create a table of values. I have an x value of 3 here, and I want to plug that x value of 3 into the function y equals 2 to the x. Well, again, because our exponent is our variable, that means that we're going to be plugging stuff into the exponent. So we're going to have 2 to the third power. Well, 2 to the third power, that simply means take 2 and multiply times itself 3 times. 2 times 2 times 2 is 8. So we end up having y equals 8. So now that we have this idea of how to do a little bit of the calculation, remember that if we have an xy table, we can then think about those values as coordinates of points. So let's go ahead and plot this point. I have a point that has an x coordinate of 3 and a y coordinate of 8. 3, 8 is going to be right here. Well, let's go ahead and do that a few more times. X value of 2, that means that we're going to have 2 to the second power. Again, notice it's the exponent that's changing here. 2 to the second is 4. So I have a point 2, 4. Well, 2, 4 is right here. 1, we would have 2 to the first power, that's simply 2. So 1, 2 is sitting right there. Now let's go ahead and do some things that go back and review some rules of exponents. So the next one we have to have is 2 to the 0 power. Remember that if you take pretty much anybody to the 0 power, you end up getting a constant back. Now, sometimes people think about the wrong constant, so you got to be kind of careful on this. Remember that pretty much anybody, other than 0, to the 0 power is going to give you the constant 1. If that's something that you remember from earlier, great. If not, make a note to yourself off to the side to remind yourself that, again, pretty much any constant to the 0 power is going to be the number 1. So we have then the point 0, 1. Let's plot that. So now that we have that then, next again, we have 3 different pieces that we need to think about rules of exponents for. So what happens when we plug in that negative 1 power? Remember that negative exponents move things. So right now, this 2 is in the numerator. My negative 1 exponent is going to move that 2 from the numerator down into the denominator. So this is equivalent to 1 divided by 2 to the positive first power. Now, I'll write it the first time, but I'm not going to write this a lot. So notice once again that we have 2 to the first. We've talked about this before. 2 to the first power is really just 2. So this is really just 1 over 2. So now that we have this then, we have another point. Negative 1, 1 half. Well, negative 1, 1 half is going to be right there. Well, let's keep going. We can have y equals 2 to the negative second. Once again, the negative exponent is going to move things. So I'm going to have a 2 to the positive second power in the denominator. 2 to the second is 4. So I end up getting that 2 to the negative second power is the fraction 1/4. Well, okay, plug that in. Negative 2 1/4, we're going to have a point right there. Negative 3, well, that's going to be 2 to the negative third, which is equivalent to 1 divided by 2 to the positive third. And we already know that 2 to the positive third is 8. So we have another point, which is going to be negative 3 1/8. So now, as you look at these points then, what you have to realize is that we have 2 very different behaviors when we look over here at the left-hand side, and then when we look over here on the right-hand side. So if you look at the right-hand side, notice that on the right-hand side, we're going up and to the right forever. That is behavior like polynomials. That in the world of polynomials, on the right-hand side, you would either shoot up forever or shoot down forever, and that's the same kind of thing that we're encountering here. Now, an exponential function shoots up forever faster than a polynomial function, but it still goes up forever. So that's the first thing you want to note about exponential functions, that one side is going to go up or down forever, And then on the other side, on the left-hand side, we have a very different behavior. So over here, notice what was happening to our y values. As we went out to the left, we weren't going down to negative infinity forever. We were getting smaller and smaller. So notice we had a little fractional value, a smaller fractional value, even smaller fractional value. And that's just going to keep on going as we go to the left. So as you look at the left-hand side of this exponential function, it does not approach infinity or negative infinity. It actually is going to be approaching 0. It's approaching the x-axis. So when you look at this left-hand side then, the behavior on the left is not like a polynomial. It's more like what we saw in the world of rational functions. So in rational functions, when we saw this kind of line that your graph got closer and closer and closer to on the left-hand side or the right-hand side, we called it an asymptote. And it's the same thing here in the world of exponential functions. We have a horizontal asymptote, and that horizontal asymptote is y equals 0. So when you look at the left-hand side of this graph, we're approaching the horizontal asymptote, y equals 0. So now that we have this idea of what the graph of y equals 2 to the x looks like, the question is, what would change if instead of y equals 2 to the x, we had y equals 7 to the x? Well, the first comment is it would still have this basic shape, where we would swoop up like this as we go to the right. Next off then, think about what's going to be happening in terms of some of our points. Some points are going to change, but some points are going to stay the same. So one of the points that we saw here on the graph of y equals 2 to the x was the point 0, 1. That point 0, 1 would still be on the graph of y equals 7 to the x. So 0, 1 is on the graph of 2 to the x. It's also on the graph of 7 to the x. Well, okay, how about the next one over? The next one over was the point 1, 2, when we were looking at the graph of y equals 2 to the x. But if I change this to y equals 7 to the x, then when we plugged in that 1, we would have 7 to the first, which would be 7. So instead of 1, 2, that would be a point 1, 7, and then it would continue from there. So now that we have this idea, we can go ahead and generalize it and say what would happen if we were looking at a graph of a general exponential function, and that general exponential function was a to the x. Well, the answer to that is it depends on how big a is. So I'm going to go ahead and start by talking about a values that are greater than 1. A values that are greater than 1, an example would be 2, is going to have a graph that looks just like the thing we just looked at. So it's going to have a general graph like this. So you'll notice that I've given you a table on your handout. Over on the left-hand side, go ahead and draw this general functions graph. And now that we have that general graph, let's talk about some of the things that are going to move forward from that graph of 2 to the x. Well, first off, I know that I'm going to have that same horizontal asymptote. So my horizontal asymptote is going to be y equals 0. And I already talked about the fact that at the point 0, 1 would be on this graph as well. Well, how about some of the other points? Well, over here, when we were looking at the graph of y equals 2 to the x, we had the point 1, 2. If it's the graph of y equals a to the x, then we're going to have 1, a. And over here, this was the point -1, 1/2 on the graph of y equals 2 to the x. On the graph of y equals a to the x, this would be the point -1, 1/a. Now that we have that information, there are all sorts of other interesting things to note as you look at your handout. So let's go ahead and take each one of those one at a time. The domain is all real numbers. The range, everything on this graph is above the x-axis. So the range has to have 0 to infinity, not including that 0. As you look at the graph, we don't have any x-intercepts, but the y-intercept is 1. The x-axis, y equals 0, is the horizontal asymptote, And then, once again, as you look at this, we have f of x equals a to the x, where a is greater than 1. When a is greater than 1, this is an increasing function. It's going uphill as we move left to right. And next off then, we have our points again, -1, 1 over a, 0, 1, 1 comma a. And then finally, just like the world of polynomials, the graph of f must be smooth and continuous. So now that we have this idea, what other kinds of things can we do with exponential functions? Well, we can do some more evaluations. So let's check out example 2.